All right. Hopefully we're all in the right place. This is Cscd 420 Automata and Compilers. I'm Dr. Chris Kane. You can call me Chris, you can call me Dr. Kane. I don't particularly have a preference. Things to know, you've found the classroom where we will be Monday, Tuesday, and Thursday. Wednesday and Friday will be down in 219. I don't know the extent to which we will be utilizing the lab capabilities too much. It was kind of outside of the purview of how I set up the class, but that's where we will be. For my office, I'm just across the way with all the other CS professors. In 334, I tried to structure my office hours around both of my classes. I teach at 9 and 12, so my office hours are between those hours. If they don't work for you, I am more than willing to work with you. Just send me an email and I can find a time to meet with you. I am most likely going to be available both of those hours between 10 and 12 in those hours every day. I'll just be in my office. If my door is open, feel free to swing by, ask questions. I am very available. I generally want that to be the case. I want you to feel like you have the support that you need to be successful in class. The TA for the class is Harley Davis. He's in the group of cubes, the graduate student cubes that are there. You can find his desk. He's on the left side, second desk in. He's also very accessible and tries to be as helpful as he can. So feel free to meet with him as well. I will try to get his office hours to you as soon as I can. One thing to note is the course is called Compilers, but the course will cover both automata and compilers. So we'll be spending about the first probably 5 to 6 weeks talking about automata and the final 4 to 5 weeks talking about how automata is applied to compilers. So you can see course description, the types of topics we're going to be covering, the associated outcomes. We will be using a textbook in here, but it is not required that you go buy it. It's easy enough to find in an older edition. I will be assigning some book problems out of it, but I will also be posting screenshots of those book problems and any associated images that you might need to Canvas along with the assignment so that you do not need to go purchase the book unless you would like to. I do recommend it, or at least having an older edition off to the side that you can reference as I go through some things. But do note that this is a theoretical, abstract math type course. I will be doing my best to strip as much of that away as possible to make it more accessible, but the more outside material that you read, most of the time, it is very proof focused, very mathematical. So just beware of, it's the math, math caution sign. This course contains math. And again, I'll try to make it as accessible as possible. Policies for me. If you send me an email, I don't want there to be any confusion as to whether I have received your email or not. So please give me 24 hours to respond. If I have not responded to you within 24 hours, that means that it slipped through in some capacity. So I guarantee responses in 24 hours. That has not happened. It's not personal. It's not intentional. It happens. I get swamped with emails. Things get forgotten. But this allows you to know that you're free to send me a ping to say, hey, please respond to this, or I need something with regards to this. But note that that means that I can't guarantee that I have a response out for you. If you email me the night before an exam, the night before something is due, I will still do my best to get to those emails, but I have a life outside of teaching. So I like to be able to do my best to separate work and life when I can. So please do your best to respect that. If you have a question, get it to me as soon as possible so that I can get a response to you before it's an emergency. I love seeing people in office hours, so please do not hesitate to swing by for office hours. You don't even necessarily have to have a question about the class. If you just want to talk about your experience as a student, what comes next for you, whether you're applying for jobs, applying for graduate school, swing by, feel free to have a conversation with me. I want to get to know you, get to know your academic interests, and help you figure out whatever your next path forward is. I want office hours to be a place where students can talk to students, students can talk to me. So I don't want it to be a scary, intimidating thing at all. I would love to see you. I also want to normalize making mistakes. One thing that I don't do in class is cold call people. I, as a student, hated it. It made me very anxious. I have pretty bad anxiety and ADD myself, so I know very much what it's like to be a stereotypical computer science student, don't want to be called on. That said, the pace of my class relies on frequent student participation. So if you are able and comfortable, I would appreciate if you have anything to say about the class, feel free to contribute. I will, again, not cold call you, but I will appreciate your engagement and involvement in the class. I expect there to be mistakes. If you say something that is not right, that's fine. That'll give me an opportunity to work with it. So expectations of students, please do try to come to class prepared and on time. I know this is a 9 o'clock class and a lot of you are commuting from a ways away. That means that it's a very early class, earlier than it feels in a typical setting. So do your best to, if you drink coffee, come to class caffeinated. I will also come to class caffeinated. I am fresh into my first cup of coffee for the day, so that's what I do. Advocate for yourself. I know that's something that's very near and dear to my heart. I hope that you are able to speak your mind about how class is going. I am always open to feedback. If you are beginning to struggle, that is not something that is unheard of, and it's something that I'm very open to working with you on. So please do reach out to me and recognize that you belong here. You deserve to be successful here, and I will do whatever I can to help you to be successful in this class. Make sure that you check Canvas and email frequently for any announcements. I've done my best to ensure that the schedule at the end of this document is the schedule that I will follow throughout the quarter. This is the first time that I'm teaching this class, so I have no idea what will actually happen. I reserve the right to move things around as needed. That's usually for your benefit, but the schedule at the bottom is for current reference and the most up-to-date due dates, and everything else with regards to the class will be posted to Canvas or sent in an email, or both. I expect people to attend class. I don't record any attendance, but especially because this class is fairly fast-paced, you'll want to be here. You'll want to be engaged with the learning process to whatever extent possible. Grading policy. We will have weekly homeworks out of the book. So 40% of your grade will be those homeworks. I expect there to be about 10 of them. I don't know what that will look like when we hit compilers, because compilers is more of a project focused topic and not so much an easy homework book problem type thing. So I reserve the right to change up and have fewer homeworks than once per week, but expect it to be weekly at the start of the course. There will be 40% of your grade determined by 4 exams. Those exams will be in weeks 3, 6, 9, and a final. I do plan to stick to that. I don't like changing exams and exam dates. So you can carve out the Fridays of weeks 3, 6, 9, and whatever day we have our final. I haven't checked that here yet. And then there will also be a compilers related project toward the end of the course that will make up 20% of your grade. I do this in all of my classes. I reserve the right to give you up to 5% extra credit. If I notice that you attend frequently, are an active participator, if you come to office hours and advocate for yourself, basically, if I know who you are at the end of the quarter and we've had conversations about your involvement in the class, then I will be happy to give you some extra credit for your involvement. If that's not the case, if you don't need that in order to be successful, then great, you're already successful. And you probably don't need the extra credit. Pretty typical grading scale. I know some professors like to make this a little bit lower for accessibility. I will always do a Passover grades at the end of a quarter just to see how I feel about grades. I will go person by person and say yes or no. Do I believe that this person earned this grade? And if the answer is more than 2 or 3 times no, then I will start curving the entire class up until I'm happy with where everybody's grades are. So this is not 100%, you know what your grade is going to be, but you know what your grade floor is going to be. I will never curve the class down from that end of quarter, but it gives me a little bit of flexibility if the quarter has been a little bit too harsh or too hard on people. One note, I call this the anti-ChatGPT part of the syllabus. I do need people to be able to perform on exams in order to pass the class, or at least in order to use it as a prerequisite or as part of your major. So I will be separately looking at exam scores. I will curve those as needed if the exams end up being too difficult, but what I'm trying to avoid is people using ChatGPT to generate answers to the 40% that is your written assignments, to generate a reasonably passing project at the end of the quarter, and then bomb all of your exams and take nothing out of the class. So I'll be looking for you to perform reasonably well on the exams, and that will give you motivation to not cheat and etc. All right. More information about attendance, assignments, projects, and exams. One thing to note on exams, as I do this for all my classes, you are free to bring a note card to exams. Otherwise, they'll be closed book, closed notes, and on paper. I don't anticipate having them really on Canvas because I feel like in order to do that, I have to stand awkwardly in the back of the classroom and watch everybody's screens, and that's a little bit more involved than I like to be, than I feel like people want me to be during an exam. So because of that, they'll be on paper, but please do bring a note card with you with any notes on it that you want. Questions so far? I do also try to keep weekly due dates. So that's for your organization as well as mine. So I will do my best for assignments to always be due on Wednesdays, and then exams to always be on Fridays. And that way you don't have to ask yourself on a week-by-week basis, when is something due in this class? So academic dishonesty, it's run very similarly to a math class. So you're expected to work on your assignments on your own. You're welcome to talk to each other about those assignments, but only at a level that you would be comfortable doing in my office out loud. What that means is you can talk to each other about very high level processes or your understanding of a particular concept, but try to keep the actual steps to solving the problem away from your friends, and that allows them to develop the tools that they will need to be successful on future exams and to be able to retain this material for the future. I've found when I've taken this kind of course, it's very interesting and it stuck with me a lot. And I feel like that is undermined a bit if you are spending a lot of time getting help from your friends and not building that understanding yourself. And then, of course, any work you submit should be a product of your thoughts. Don't copy any answers from the internet. I have some fun stories. Don't submit screenshots of Chegg with Chegg on the screenshot. I've been there, I've seen it. Other than that, everything else is Eastern policy to include on a syllabus. If you have any questions about any of this material, please don't hesitate to ask. I would love to discuss it with you. I will also happily work with you if you have any disability accommodations I want to make sure that you have the opportunity that every other student does in the class to be successful. Let me know what I can do for you. I think that's everything I wanted to go over. Any questions? Anything that I missed? Any typos you spotted? Very quiet, spooky. All right. So my plan for the very first day is just to go over some review. Since it's a math-focused class, I wanted to make sure that we have the opportunity to go over some of the material that you will need if you see some external material. Again, I will try to strip as much of this away as I can, but I can't guarantee that I strip it all away. So the more prepared we are, the better. I think this should be everybody in here, but who's taking discrete math? Just about everybody. Who remembers everything from discrete math? Right. It's one of those classes where I expect that a lot was covered, and so it will be good to go over some of that material. Question?
Will you have the slides anywhere for us to?
Yes, I do plan to post slides to Canvas, so you do not need to take word for word notes. I always say that it's better to pay attention to what I am saying than exactly word for word what's on the slide. You will have access to what's on the slide. So yes, my plan is to post whenever I do record class. My plan is to figure out a way to post that recording. I don't know where it will be. Canvas has limited total file size for the quarter, etc. So I'll post to YouTube, or I'll figure something out. But yeah, slides will be available. Thank you for the question. All right, so we are going to cover automata theory. Who's heard of automata theory or knows at all what I'm talking about when I say automata theory? Excellent. This will be fun. We will also talk about formal languages and grammars. We'll talk about a very abstract component, which is just computability. What can be computed? What cannot be computed? We will talk about some advanced computational complexity, building on any data structures material, and talk about computational complexity that you had there and how it applies to computability. And we'll take all of this once we've seen it in an abstract form and apply it to how it is most frequently used in computer science, which is building a compiler or an interpreter. So if we take all of this, everything that we're planning to cover this quarter, this material makes up the theoretical foundation of computer science, which is a really exciting topic, I find. So it asks questions like, what can be done by computers? Just in a general sense, what capabilities do computers have? What can they do? What can't they do? And also, what can be done by computers in practice? So we'll try to bridge that gap between theory and practicality. So we'll start with some basic definitions. First is an automaton. It's a construct possessing features of a computer. It's kind of an abstract computer. So just like a computer running a program, it can accept input. It can produce output. And depending, there are different kinds of automata. Some of that automata has access to some temporary storage. And just like a computer, it can make some decisions while it's transforming that input into output. You'll get a much better idea as we start talking about different kinds of automata. We also need to define what a formal language is. You can think of this as an abstraction of a programming language. So as part of this, we have an alphabet, a set of legal symbols. We have rules of formation. We need to figure out, we have these characters, how can we combine these characters into statements? This is very similar to any spoken or written language like English. We have characters, we combine those characters into words, we combine those words into sentences. And if we follow the syntax and semantics of the language, what we end up with is meaning. It's very similar to binary, which at its core is what computers understand. Binary has a set of characters. Those characters can be combined into bytes, and those bytes in sequence have particular meaning at a machine code level. All right, we're going to put a pause on this for a moment because we're going to come back to it probably starting tomorrow, but we're going to dive into, to be able to explain and explore some of these concepts, we need to review elements of discrete math. So the most important is probably sets and set notation. So a set is a collection of elements with no structure other than whether or not an element is a member of that set. Order does not matter. Multiplicity does not matter. So we surround sets by curly braces. Who can recall the symbol that we use to indicate that an element is a member of a set?
It's like a C with a line in them.
Yeah. We say X is a member of set S. So X is the element, that's the membership symbol, and this S stands for a set. How do we indicate that X is not a member of set S?
Slash through it.
Slash through it, yes. How can we refer to sets without exhaustively listing all of the elements of that set? Some sets are infinite sets, like for instance, the set of all positive integers. The set of lowercase letters. I don't necessarily want to write out 26 letters. How could I do that? How could I represent that without exhaustively listing them all?
Give the symbol for the set, like S.
If it has a symbol, yeah. Like for instance, the natural numbers is a hollow N. But you can also use an ellipse. If, for instance, you wanted to represent all lowercase letters, here is one way you might do that. A, B, and at some point you recognize the pattern. If you include an ellipse, it says all elements that are part of this natural collection. If you wanted to list the positive even integers, you could do something like 2, 4, 6, ... meaning that this is an infinite set with an infinite number of elements, and now you've portrayed the idea of all of the elements this set contains with a limited number of characters. Questions so far? About union, intersect, and difference. Who remembers what those mean? Hunter.
Union is the between two sets of things they have in common, or not. It's all of the elements in both sets. An intersection is the things that are in both sets. And the difference, something else.
Who remembers set difference? Yeah.
I might get this wrong, but it might be the things that match, you cancel them out, and then whatever's left over, it's.
Yeah, it's all the elements of the first set that are not in the second set. So union, it's all members X. The colon stands for such that, all elements X such that X is an element of set 1 or X is an element of set 2, and that's an inclusive or, not an exclusive or. So they can be in one or the other or both. The intersect, all elements X such that X is in both set 1 and set 2. And then the set difference says that all elements that are in set 1 that are not in set 2. Does that make sense at an intuitive level? So we talked about a little bit what that means in English. Do we want an example? We can draw an example. What is in the union of these two sets? Everything in either?
Yeah.
How many copies? We noticed that 2 is in both S1 and S2. Should we write 2 copies within this set? It actually doesn't matter whether we do or don't. It's the same set. But yeah, in general, you want to reduce the complexity as much as possible. So you could put 2 copies of it, but it has no meaning once you have additional copies. It's either a member or not a member. So we will write 1, 2, 3, 4, 5, 6, and 8. How about the intersect? 2 is in both, 4 is in both, no other element is in both. 2 and 4. How about the difference?
1, 3, 5.
All elements that are in the first set that are not in the second set. So 1 exists here and not here. 3 exists here and not here. 5 exists here and not here. Questions about this? Okay to make it all go away? Question?
So if. In an application of this, if you care how many sets, like 2 and 4, you wanna keep track of frequency, do you have to use something other than sets then?
Yes. Yeah, because sets are only going to care whether or not they're an element, yes or no. So if we care about the number of sets that something is in, yeah, we need to use something else. Excellent question. Anything else? All right. We have this idea of a set complement. Does anyone remember what a set complement is? We first need to define a universe. So a complement of a set is everything that is in the universe of that set that is not in that set. So maybe we have a set representing all odd positive integers. We have another set representing 1, 3, 5. Then the complement of the set 1, 3, 5 would be 7, 9, 11, ... The rest of the odd positive integers. So this uses this concept of a universal set. The universal set will contain every possible element, but can be further specified to be every element of a particular class, like odd positive integers, or students in this class, or anything else. Make sense? Questions? We can define the empty set as a set that contains no elements. We can come up with a few rules with regards to the empty set. If you union a set S with the empty set, it's the same thing as taking the set difference of S and the empty set. You just get S. If you intersect some set S with the empty set, then the result is the empty set, which makes sense. The elements in common between a set with some number of elements and a set with nothing is going to be nothing. If you take the complement of the empty set, you get the universal set. Everything not in the empty set is going to be everything in the universal set. However, we're defining that universal set. If you take the complement of a set S, you get back to where you started. Everything not in the complement is going to be itself. Does that make intuitive sense? Question?
Is union usually a minus on like, because you have there, you have the set minus an empty set. But union was a sum.
It is, but this is saying that when you take the second one being the empty set, that they're equivalent to each other. The union with the empty set is the same as the difference. But that's the only set for which that's going to be true. Otherwise, there's going to be some differences between those definitions. Who remembers De Morgan's laws? So in set notation, we have the complement of the union is equal to the intersect of the complements. And the complement of the intersect is equal to the union of the complements. Does this intuitively make sense? I feel like this requires a little bit of explaining for this to intuitively make sense. Can anyone attempt to intuitively explain the first of these two De Morgan's laws?
I guess it just makes intuitive sense when you kind of word it out like a sentence. So if it's not this nor that, that kind of sounds like not this and not that.
Okay, I like that, using English and logic combined to try to determine the equality of two ways of phrasing the same idea. Anyone else have any other intuitive approach? So this is a very good idea to use the concept of a union with the English word or, although we have to further specify, since or is ambiguous, whether we're explaining an inclusive or an exclusive or. Do people remember the difference between inclusive and exclusive or? Worth going over the difference just because. So we have or, let's say, so we have well, we'll just call it P and Q because that's usually what is used here. True, false, false, true, false, true, false. So every combination of true and false here, this would be, it's in set one or in set two, which is what we mean by P or two or Q. So I guess we can say X member of S1, X is a member of S2. So inclusive or says if it's in one or the other or both. So we get a true, 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 and false. Exclusive or says it's in one or the other, but not in both. So we get very similar looking. But the main difference is here where both are true. Inclusive or says yes, it's true. Exclusive or says no, it's false. And that's the only difference. So when we use union, we're using this concept of inclusive or. Because if it's in both set one and set two, then it's in the union of set one and set two. So this represents the union. And XOR is not exactly specified in this current state. So now can we find some intuitive way of stating, all right, so if it's not in this, if it's not in the union, then what case do we have to be in?
It's not in either of the sets.
Yeah, so we have to be talking about this. So this is saying that it's not in S1 union S2. If it's in S1 union S2, then it's in one of these three categories. So for it to be in the complement, it has to be here. That's the only case we can be talking about. On the other hand, what is the intersect of not being in S1 and not being in S2? So not being in S1, we're in here. And not being in S2, we are here. So in which line are both elements circled? It's still only here. So you can use an intuitive approach, you can use a logical approach, you can show that De Morgan's law is true using any of those approaches, but I prefer an intuitive approach or a logical approach. And I urge you that if you don't understand some concept like this, try to take an intuitive approach to it, or try to draw it out in some kind of form to help you with that process. Because if you just see something as a rule and try to memorize the rule, then you forget it immediately because it's not useful or relevant and it doesn't really make sense. It's just something that somebody is telling you is true, and that's never good enough. So we could go through the same for the second one, but I'll leave that for an exercise. Any questions about De Morgan's laws? All right, the next thing we care to discuss is the concept of cardinality. Cardinality tells us how many elements are in a set. It's just the count of how many things are in here. So if we have a set ABC, we will specify the cardinality as, think of it as in absolute value. The size of set S is 3. Next thing, subset. We'll say we have some set S1. It's a subset of another set S if every element in S1 is also an element of S. We write it like this. It says that S1 is a subset of S. It's very similar to the mathematical concept of less than or equal to. I like to try to draw a parallel between those ideas. If you have a number that's less than or equal to another, then it could either be less than or it could be equal to. So if it's a subset, then it's going to have some of the elements or all of the elements of S. But it can't have an element that S does not have. Just like we can specify strictly less than, we can also have a proper subset that says that now we take out equality. They cannot be exactly the same set, but S1 now must have some proper subset of the elements of S, meaning that it has some of the elements, but not all of the elements. And it still cannot have an element that S does not have. As an example, let's say we have simple set A, B, and C. What are all of the possible subsets of S?
Combinations of A, B, and C. And the empty set.
Yes, so the empty set is a subset. We could have A, we could have B, we could have C, we could have A and B, A and C, B and C, or A and B and C. How about proper subsets?
Get rid of the last one.
Yeah, this is the only one that is part of the subset that is not part of the proper subset because we can't have strict equality between the proper subset and the original set. But as soon as we introduce some other character, if we put a D in any one of these subsets, then it's no longer a subset and it's no longer a proper subset. Because there's an element in here in one of these subsets or proper subsets that's not in the original set. So it's not a subset, not a proper subset. Make sense? Questions? Concerns? All right, next one is the power set. The power set is the set of all possible subsets. I just wrote out all of the possible subsets for this, but here is the terminology for the power set. Why do we think we write 2 to the S? Why does that make sense?
I mean, the amount of subsets is 2 to the power of the cardinality of S.
Yeah, so if we wanted to know the cardinality of this, how many sets are there in this set of subsets? We can count them. We have 1, the empty set, 2, 3, 4, 5, 6, 7, 8. What was the number of elements in the set? 3. What is 2 to the third? 8, which is the number of elements in the power set. So this is what makes this terminology make sense. It's just the number of elements in the power set. Next one, the Cartesian product. If we have 2 sets, we want to be able to create a set of tuples. What is the definition of a tuple? Is that a tuple?
Yes.
Yes. We call a tuple an ordered pair. Now order matters. X comes first, Y comes second. So a Cartesian product, if we have 2 sets, we want to build all the possible tuples such that the first element of the tuple is an element of the first set. And the second element of the tuple is some element of the second set. So mathematically, we say S1 cross S2. It's going to be all tuples XY such that X is a member of set 1 and Y is a member of set 2. An easy way, easy example for a Cartesian product, if we have S1 what would all of the possible tuples in the Cartesian product be?
A1.
A1, A2, A3, yeah, so we'd have A1, A2, A3, and there'd be 9 of these, B1, B2, B3, C1, C2, C3. Note that if there's the same element in both, you'll just want to duplicate it. So if A were in both sets, you could have the tuple AA, and that's now different because of tuple multiplicity does matter. So you can absolutely have repetition here if an element is in both sets. Question?
Do you want the Cartesian product written as a set or a matrix?
Doesn't particularly matter. I like it as a set. It's the set of tuples, but if you write it as a matrix, a matrix implies that there's a position like, and for some purposes that would be suitable. If you needed, you know, row 2, column 1 of the matrix represents a particular, like you need a particular ordering for it, then you can certainly put it in a matrix and then you get that ordering. And as a set, you don't really get that. So the matrix has a bit more information in it than the set, but it depends. So order matters in tuples. Last thing we will quickly cover, definitions of functions and relations. We have a bit more to cover on relations, but we'll stick to functions for the moment. So we're going to assign every element from one set to an element from another set. If you can do that, then you have a function with a couple other specificities. Domain of a function, all the elements of the first set. Range, all the elements of the second set. The codomain, which is frequently misrepresented as the range, is just all elements of the second set, but the range are the elements of the second set. So sorry, the codomain is just the elements that have some element mapped to it. So if we had here we have elements of one set on the left, elements of another set on the right. It is a function if every element on the left is mapped to some element on the right. But it cannot have multiple mappings, so you can't do something like this. That's not a function. But every element on the left must be mapped to something on the right, but it could be that all of these map to the same location. This is still a function. But now this gets us the difference between the range and the codomain. The codomain is everything here, so this and here we have the range. All of the elements that have some element of the first set mapped to it. All right. I think that's everything that I'm planning to go over, and I'm right on time. Wild. We will come back here tomorrow. We will start talking about automata theory. It'll be actual stuff you haven't seen before. Morgan's law.